Hello, students. Imagine you're riding a bike. At first, you're at rest. Then you start pedaling and pick up speed. You're accelerating. But then you see a red light and press the brakes. Now you're slowing down, or in physics terms, you're experiencing retardation. This change in how fast something is moving, either speeding up or slowing down, is what we call acceleration. And when this change causes the body to slow down, we call it retardation or negative acceleration. Whether it's a car starting, a ball thrown upwards, or a rocket launching into space, acceleration is everywhere. Let's define it properly. Acceleration is the rate of change of velocity with time. In simpler terms, how quickly an object's speed or direction is changing. Mathematically, we write A equals open bracket v minus u close bracket divided by t, where v is the final velocity, u is the initial velocity, and t is the time taken. The SI unit of acceleration is meter per second squared, written as n per second square. It's a vector quantity, so direction matters. If the final velocity is less than the initial, then the acceleration becomes negative, and that's what we call retardation. Let's apply this in real examples. Example 1. A car starts from rest and reaches 20 meters per second in 10 seconds. We calculate A equals open bracket 20 minus 0 close bracket divided by 10. That gives 2 meters per second squared. Example 2. A car moving at 25 meters per second comes to a stop in 5 seconds. Now A equals open bracket 0 minus 25 close bracket divided by 5. That gives minus 5 meters per second squared. A positive value means acceleration. A negative value means retardation. The object is slowing down. This is how vehicles speed up or stop smoothly with controlled acceleration. Here's something very important. Acceleration alone does not determine the direction of motion. That's the job of velocity. Acceleration only tells us whether the velocity is increasing or decreasing. So if a body is moving forward and speeding up, acceleration is in the forward direction. But if it's moving forward and slowing down, acceleration is acting against the direction of motion, hence retardation. Understanding this helps us interpret motion precisely, especially when analyzing graphs or solving motion problems. Now let's explore the types acceleration can be uniform or variable. In uniform acceleration, velocity changes by equal amounts in equal time intervals. For example, a free-falling ball accelerates uniformly under gravity. In variable acceleration, velocity changes unevenly like a car in traffic. Uniform acceleration is easy to calculate and predict, but variable acceleration is more common in real life and needs advanced tools like graphs to analyze. When a body falls freely under the Earth's gravity, it experiences acceleration due to gravity, denoted by g. The standard value is 9.8 meters per second squared, directed downward. So, a freely falling object increases its velocity by 9.8 meters per second every second. For example, after 1 second, v equals to 9.8 meters per second. After 2 seconds, v equals to 19.6 meters per second. After 3 seconds, v equals to 29.4 meters per second. If the body is thrown upwards, it slows down at the rate of minus 9.8 meter per second squared. That's retardation due to gravity. Here's an amazing fact. The value of g doesn't depend on the object's mass. A hammer and a feather fall together in a vacuum. Let's now understand the velocity-time relation in a uniformly accelerated motion. When a body is moving with uniform acceleration, its velocity keeps changing at a constant rate. The velocity after a certain time t is given by the first equation of motion, v equals u plus a into t, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is the time taken. To find the distance or displacement covered during this motion, we use the second equation of motion, s equals u into t plus 1 by 2 into a into t squared. Here, s is the displacement, u is the initial velocity, t is time, and a is the uniform acceleration. Now, if the direction of motion and the direction of acceleration are the same, the body speeds up. This is called acceleration. But if the direction of acceleration is opposite to the direction of motion, the body slows down. This is called retardation, or negative acceleration. So these equations help us predict how the velocity and position of an object change under uniform acceleration. Let's wrap up with a quick summary of acceleration and retardation. Acceleration tells us how quickly the velocity of a body changes over time. When this change happens in the opposite direction of motion, it's called retardation or negative acceleration. It's important to remember that acceleration is a vector quantity, which means it includes both a magnitude and a direction. We also differentiate between uniform acceleration, where the rate of change is constant, and variable acceleration, where it changes with time. These concepts help us explain different real-world motions. One special kind of acceleration is acceleration due to gravity, a nearly constant value near the Earth's surface. It plays a key role in understanding falling objects and planetary motion. Finally, acceleration isn't just theoretical. It helps us explain practical phenomena like the motion of vehicles, projectiles, elevators, and even powerful space launches. Understanding how things speed up or slow down brings us one step closer to decoding the world of motion.